Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 3, Part 2, Entropy, Lecture number 11. Myself, Dr. Nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. The contents for this topic are some important relationships involving entropy, then principle of increase of entropy. So, mathematical expression of the second law, Q is equal to TdS for reversible process, because dq by dt is equal to ds, that is what is studied. So, you can write Q is equal to T into ds for a reversible process, then Q is less than TdS for an irreversible process. So, two very important relations from the second law involving entropy. The above equations may be regarded as the analytical expressions of the second law of thermodynamics. Okay. Now, important relations for a pure substance involving entropy. The first law for a closed system is given by del Q is equal to dE plus del W. So, all of you know, I won't explain these things. If the kinetic and potential energies are very small, the equation 1 can be written as, now here if the kinetic energy and potential energy is neglected, then dE becomes equal to du. This is all of you studied in the first law chapter. So, for a reversible process, del Q is equal to TdS, then equation 2 becomes, so here del Q you have to replace by TdS, so TdS becomes equal to du plus del W. The work done at the boundary of a system for a reversible process is del W is equal to PdV. So, this also you studied. So, I am just recalling whatever you studied earlier. Okay, substituting in equation 3, you get TdS is equal to du plus PdV. Now, in place of dq you substitute TdS, in place of dE neglecting kinetic and potential energy you substitute du, and only considering only displacement work, in place of del W you can substitute it as PdV. Or in specific terms, so this is specific quantity, so you can write it as TdS is equal to du plus PdV. So, the ds is a change in specific entropy, this is a change in specific internal energy. Okay, this is specific volume, change in specific volume. So, from equation 5 we realize that it involves only changes in properties and involves no path functions. You see, there is no path function involved in that expression. So, therefore, we conclude that this equation is valid for all processes, both reversible and irreversible, and that it applies to the substance undergoing a change of state as a result of flow across the boundary of the open system as well as to the substance comprising closed system. That means the equation 5, okay, you can apply it for reversible process, you can apply it for irreversible process, you can apply it for the open system as well as you can apply it for the closed system. Since H is equal to U plus PV and DH is equal to du plus D of PV, so in the differential form. So, all of you know that enthalpy is equal to internal energy, sum of internal energy plus product of pressure and volume. So, in the differential form you can write dH is equal to du plus D into or differential of PV. Okay. So, we get du is equal to dH minus D of PV. Okay. So, if you substitute this in equation 5, we get ds is equal to dH minus VdP divided by T, or based on the unit mass, if you write, or in terms of specific quantities, you write as ds is equal to dH minus VdP by T. Okay. Now, first and second law combined relations. Del Q is equal to dE plus del W. So, this equation holds good for any process, reversible or irreversible, and for any system. Then del Q is equal to du plus del W holds good for any process undergone by a closed stationary system. Okay, when the system is considered to be stationary. Then del Q is equal to du plus PdV holds good for reversible process undergone by a closed system when PdV work is present. So here it can be any other work interactions also, but here it is only PdV work. And del Q is equal to TdS, true only for a reversible process. TdS is equal to du plus PdV. This equation holds good for any process, reversible, irreversible, undergone by a closed system, since it is a relation among properties which are independent of the path. So this already we discussed in the previous slide. And TdS is equal to dH minus VdP. So this equation also relates only properties of the closed system. So there is no path function term in the equation, hence the equation holds good for any process. Next we will study the principle of increase of entropy. So let us find out the entropy change for the system and surroundings together, so when there is some heat interaction. So consider a system at temperature T, you can see here, giving out some amount of heat del Q to the surroundings at temperature T0. So because of this heat transfer, so there will be some entropy change for the system as well as entropy change for the surroundings. So using the principle of increase in entropy, the entropy change for the system is greater than or equal to minus del Q by T. And for the surroundings, so it is del Q by T0, because the amount of heat divided by the temperature at which the heat transfer takes place. So for the system the temperature is T, for the surroundings the temperature is T0. Now the total change of entropy for the combined system is nothing but ds system plus ds surroundings. So you will get it as greater than or equal to minus del Q by T plus del Q by T0. Or in other words, you can write as ds system plus ds surroundings is equal to, greater than or equal to del Q. Now if you take del Q outside the bracket, so inside the bracket you get a term minus 1 by T plus 1 by T0. Just simplification of the last equation from the previous slide. Now the same conclusion you can draw for the open system as well, because the change in entropy of the system would be this is the open. Suppose if you have an open system, so the entropy change is nothing but it is greater than or equal to minus del Q by T plus also the entropy of the fluid entering into the system minus the entropy of the fluid leaving the system, because already you studied under steady flow energy equation. So in an open system, so fluid mass or elementary mass enters into the system and also leaves the system. So here delta Mi is taken as that elementary mass entering into the system, and delta Me is the elementary mass leaving the system. Now change in entropy of the surroundings for this open system. This is the entropy change for the open system. Now it is interacting with the surrounding. So for the surrounding, the entropy change can be written as ds surroundings is equal to del Q by T0. Now it is minus becomes plus, and this plus becomes minus here. So every term changes, because whatever happening plus for the system becomes negative for the surroundings, and whatever happening negative for the system becomes plus for the surroundings. So sign changes here, you have to note. But first term, you see the denominator it is T0, okay, but here it is T, because you have to consider the absolute temperature at which this heat transfer takes place. Now if you combine or if you add the system plus surroundings entropy change together, so you will get minus greater than or equal to minus del Q by T plus del Q by T0, which is same as this. This is the previous expression of this. Now if you take del Q outside, you will get the same expression. That means for the closed system as well as the open system, so the entropy change of the system plus surroundings will be given by the same expression. So you can write ds system plus ds surroundings greater than or equal to del Q into minus 1 by T plus 1 by T naught. Now you have to find out whether this term is positive or negative. So that depends on whether T is greater than T naught or T naught is greater than T. Now as all of you know, in this case T is greater than T naught because T is a higher temperature, T naught is a lower temperature. So when T becomes greater than T naught, all of you have to understand, you see T becomes greater than T naught, the term 1 by T, you see 1 by T becomes less than 1 by T naught. In the sense 1 by T is a smaller number, 1 by T naught is a larger number. Now look at the sign involved. So 1 by T is minus, means this is minus, less quantity. 1 by T naught is plus, so is a larger number. So the difference is always a positive quantity. That is, it is greater than 0. If this quantity is greater than 0, see if this quantity it is greater than 0, positive, then if it is multiplied by this, so that is also greater than 0. Okay, so you can write ds system plus surroundings therefore greater than or equal to 0. So this means that process involving an interaction of a system and its surroundings will take place only if the net entropy change is greater than 0 or in the limit remains constant. So this is the condition that a process has to condition for a process to take place between the system or any interaction to take place between the system and the surroundings. The net change in entropy has to be greater than or equal to 0 and the entropy attains maximum value when the system reaches a stable equilibrium state from a non-equilibrium state. So with this I conclude this lecture number 11 and will continue in the lecture number 12. Thank you.